Jupiter is often described as a gas giant, a massive planet made mostly of hydrogen and helium, spinning in the outer solar system. The fifth planet from the Sun, the largest in our planetary family, but almost nothing about it behaves the way a gas giant should. This is not about size, it is not about composition. It is about fundamental physics that do not align with what we observe. And the more closely we examine Jupiter, the more contradictions emerge. We will get to why. But first, you need to understand what should be happening. A planet made of gas should behave predictably. Gravity pulls inward. Pressure increases with depth. Heat dissipates over time. The system stabilizes. Jupiter formed over 4.5 billion years ago. By every conventional model, it should have reached thermal equilibrium long ago. What we observe instead is a planet radiating nearly twice the energy it receives from the Sun. This is not a small discrepancy. Jupiter emits approximately 67% more energy than solar radiation can account for. That energy has to come from somewhere. The problem is identifying a source that can sustain this output for billions of years. The conventional explanation involves gravitational contraction. As Jupiter slowly compresses under its own mass, gravitational potential energy converts to heat. This process is well understood. It occurs in stellar formation. But Jupiter is not a star. It never achieved the core temperatures necessary for fusion, and the rate of contraction required to produce this excess heat does not match observed structural changes. There is also helium precipitation. Helium droplets may be falling through Jupiter's interior, releasing energy as they descend. This is plausible. It aligns with certain atmospheric observations, but we have no direct measurements of Jupiter's deep interior. The mechanism remains theoretical. What we know with certainty is that Jupiter is an active heat source. What we do not know is why it has not cooled. The interior presents another violation. At depth, hydrogen should transition to a metallic state. Under sufficient pressure, electrons detach from atoms and move freely. The substance becomes electrically conductive. This is not controversial. Laboratory experiments confirm that hydrogen metallizes under extreme conditions. Jupiter's core pressure exceeds 40 million Earth atmospheres. Metallic hydrogen should exist there. Models predict a thick shell of it, surrounding a possible rocky core. But we do not know where this transition occurs. We do not know how abrupt it is, and we do not know what lies beneath. The Juno spacecraft has measured Jupiter's gravitational field with extreme precision. Those measurements reveal asymmetries. The planet is not uniform. Its mass distribution is uneven in ways that suggest complex internal layering. The core may not be sharply defined. It may be diluted, dissolved into the surrounding envelope. This should not occur. A planet's core forms first. Heavy elements sink, lighter materials rise. Differentiation is a basic consequence of gravity. Jupiter appears to violate this. Or the core is there, but diffused in a way that current models cannot reproduce. We simply do not have enough data to resolve it. Then there is the magnetic field. Jupiter generates the strongest planetary magnetic field in the solar system. It is nearly 20,000 times stronger than Earth's. This field extends millions of kilometers into space. It traps charged particles. It creates radiation belts so intense they can damage spacecraft electronics within hours. Magnetic fields require motion, specifically the motion of conductive material. Earth's field is produced by liquid iron circulating in the outer core. Jupiter has no iron core of that kind. Instead, its field is generated by convecting metallic hydrogen. This should produce a dipole field, a simple north-south structure aligned roughly with the planet's rotation axis. What we observe instead is a field with significant irregularities. Juno's magnetometer data revealed that Jupiter's magnetic field is highly non-dipolar. There are localized regions of intense field strength near the equator. There is a patch of weak field in the northern hemisphere. The field structure is asymmetric in ways that suggest the dynamo mechanism is far more complex than anticipated. Earth's magnetic field reverses polarity every few 100,000 years. We do not know if Jupiter's field does the same. We do not know what drives these asymmetries, and we do not know how stable the configuration is. The atmosphere introduces further problems. Jupiter's cloud bands are driven by differential rotation. The equator rotates faster than the poles. This creates shear. Winds blow in alternating directions at different latitudes. Speeds exceed 400 kilometers per hour in some zones. These winds should be shallow. Atmospheric circulation on Earth is confined to the troposphere, a thin skin of gas above the surface. Jupiter has no surface, but the same principle should apply. The winds should be limited to the outermost layers. Instead, Juno's gravity measurements indicate that the jet streams extend thousands of kilometers deep. They penetrate far below the visible cloud deck, possibly reaching depths where hydrogen transitions to a fluid state. This requires enormous energy. Maintaining deep circulation against friction and pressure gradients is not trivial. The energy cannot come from solar heating alone. The sun's influence diminishes rapidly with depth. So either Jupiter's internal heat is driving these winds, or there is another mechanism we have not identified. And the winds do not decay. They have persisted for as long as we have observed them. The Great Red Spot, a storm larger than Earth, has been continuously active for at least 200 years, possibly far longer. On Earth, hurricanes dissipate within days. They require a warm ocean surface to sustain them. Once they move over land, they weaken rapidly. Jupiter's storms do not weaken. They do not have a surface to disrupt them, but they also do not have an obvious energy source. The Great Red Spot sits in a region where upwelling and downwelling atmospheric currents interact. It appears to feed on smaller storms, absorbing them and growing temporarily larger. But we do not know why it remains coherent. We do not know what prevents it from dissipating into turbulence. Recent observations suggest it is shrinking. Over the past century, its diameter has decreased by roughly 50%. Whether this is part of a cycle or an irreversible decline is unclear. The storm may disappear entirely within a few decades, or it may stabilize. We have no predictive framework. The magnetosphere creates additional anomalies. Jupiter's magnetic field does not simply extend into space. It interacts with the solar wind, forming a vast magnetosphere that stretches far beyond the planet. On the side facing the sun, the magnetosphere is compressed. On the opposite side, it extends into a tail that reaches past Saturn's orbit. Within this magnetosphere, charged particles are trapped. They spiral along magnetic field lines, creating intense radiation belts. The problem is the source of these particles. Some come from the solar wind, but a significant fraction originates from Io, one of Jupiter's moons. Io is volcanically active. It ejects material into space at a rate of roughly 1 ton per second. Much of this material becomes ionized and absorbed into Jupiter's magnetosphere. Io's orbit lies within the densest part of the radiation belt. The interaction between Io and Jupiter's magnetic field generates electrical currents exceeding 3 million amperes. These currents heat Io's interior, driving the volcanic activity that feeds the system. This is a feedback loop. Io's volcanism sustains the magnetosphere. The magnetosphere sustains Io's volcanism. But we do not know how long this has been occurring. We do not know if the system is stable or gradually evolving toward collapse. And Io is not the only source. Europa and Ganymede also contribute material. Each moon interacts with the magnetic field in different ways. Europa may have a subsurface ocean that generates its own magnetic signature. Ganymede has an intrinsic magnetic field, the only moon in the solar system known to possess one. These interactions are not well understood. The magnetosphere is not a passive structure. It is dynamic, variable, and coupled to processes occurring across multiple moons. Then there is the question of formation. Jupiter should have formed where the solar nebula was cold enough for volatile compounds to condense, beyond the so-called ice line. This is consistent with its composition: hydrogen, helium, water, ammonia, methane. But models of planetary migration suggest that Jupiter did not remain in its original orbit. Gravitational interactions with the protoplanetary disk may have caused it to spiral inward, possibly reaching the inner solar system before reversing course and settling into its current location. This migration would have disrupted the formation of the inner planets. It may have scattered planetesimals. It may have prevented a planet from forming in the asteroid belt. Evidence for this comes from the architecture of the solar system, the spacing of the planets, the distribution of asteroids, the orbits of certain distant objects. But the timing is uncertain. The mechanism is debated. and the consequences for Earth's formation are not resolved. If Jupiter migrated inward and then outward, it influenced the delivery of water to the inner solar system. Comets and asteroids were scattered. Some may have collided with the early Earth. Without Jupiter, Earth might not have oceans, or it might have formed differently, or not at all. We infer this from simulations, not from direct observation. The gravitational influence extends further. Jupiter shapes the orbits of comets. It captures some into short-period trajectories. It ejects others into interstellar space. It deflects incoming objects that might otherwise collide with Earth. This has been described as a shield, a protector, but the effect is not simple. Jupiter also perturbs objects, sending some toward the inner solar system. Whether Jupiter has increased or decreased the impact rate on Earth over geological time is still debated. The Trojan asteroids occupy stable regions along Jupiter's orbit. These are gravitational equilibrium points where the pull of the Sun and Jupiter balance. Thousands of objects cluster there. These Trojans may be remnants from the early solar system, pristine samples of material that predates planetary formation, or they may have been captured later. We have sent a spacecraft to study them. It will arrive soon. We will learn more. But the mere existence of these populations indicates that Jupiter's gravity has structured the solar system in ways we are still mapping. Jupiter also emits radio waves, decametric emissions, bursts of radiation at frequencies between 10 and 40 megahertz. These were first detected in the 1950s. They were unexpected. Planets were not thought to generate radio signals of this kind. The emissions are not constant. They are sporadic, intense, and correlated with the position of Io. As Io moves through Jupiter's magnetic field, it generates electrical currents. These currents accelerate electrons. The electrons emit radiation. But the process is not fully explained. The emissions are far more intense than models predict. The beaming pattern is complex. The signals are polarized in ways that suggest highly organized magnetic field structures. We have observed similar emissions from other planets. Saturn produces them, Uranus and Neptune as well, but Jupiter's are the strongest. And they reveal that planets can generate electromagnetic phenomena that were once considered the exclusive domain of stars and pulsars. All of this returns to a central issue. Jupiter is not behaving like an inert ball of gas. It is radiating excess heat. It is driving deep atmospheric currents. It is generating a complex magnetic field. It is interacting with its moons in ways that sustain geological activity across millions of kilometers. And none of this was expected. The models we use to describe gas giants were built on assumptions: thermal equilibrium, hydrostatic balance, simple convection. These assumptions work for stars. They work reasonably well for smaller planets. They do not work for Jupiter. Every spacecraft we send returns data that complicates the picture. Voyager revealed the atmosphere's complexity. Galileo measured the helium abundance and found it lower than predicted. Juno mapped the interior and found asymmetries we cannot yet explain. Each mission answers some questions. Each mission generates new ones. And Jupiter is not unique. We have discovered thousands of exoplanets. Many are Jupiter-sized. Some orbit close to their stars. Others are far out, like Jupiter. We do not know if they behave the same way. We do not know if the anomalies we observe at Jupiter are common or exceptional. We are using Jupiter as a template, a reference point. But the template does not fit the observations. The problem is not that Jupiter is strange. The problem is that we expected it to be simple.